Hey, welcome again. Let's talk about CCA security. And just quickly review the definition, which is pretty simple because CCA security is just CPA security, except that we allow the adversary to also query for decryptions of ciphertext that he chooses. So A would be allowed to specify any ciphertext C, send it to the challenger would use its secret key to run the decryption algorithm and send that result back to A. The only restriction for A would be that it can't ask for decryption of the challenge ciphertext. Because if we didn't make this restriction, then any adversary could always just ask for decryption of the challenge ciphertext and then pick the correct bit with probability 1. But other than that, we allow him to basically query for any decryptions. What does that model in practice? So the idea would be that in the CPA, when we came up with CPA the idea was that maybe an adversary would be able to influence what kinds of messages are encrypted. So the idea would be, if we have the sender Bob here, that CPA basically said, okay, if we can influence Bob to send certain messages, then maybe we can break the encryption scheme. And we want to have a security model that kind of covers this. And now for CCA, the idea is, hey, what if Eve here is also able to send arbitrary ciphertext to Alice and then maybe a little bit observe about how Alice behaves after decrypting this ciphertext. So CPA is kind of handling what if we can make someone encrypt something, and CCA is kind of handling what if we can make someone decrypt something. And if you think about it, it's a pretty realistic scenario that Eve, being on the wire here, would be able to just send arbitrary ciphertext to Alice, and Alice would decrypt them, because Alice would assume they would be from Bob. Now, obviously, in reality, we don't have a perfect decryption oracle that our adversary may have, right? Because this would kind of defeat the purpose. So if Alice would actually provide a decryption oracle to Eve in this real-life scenario here, then, Eve can just read all of the messages. So it doesn't really make sense then. So Eve may not get a perfect decryption oracle in practice, but maybe something different. One typical scenario would be that actually Eve may be able to know whether or not, after Alice decrypts the ciphertext, whether or not the message inside of it is well formed. So let's say it's a valid JSON document. And then whenever Bob sends a message, Alice would know, okay, it's a valid JSON document, because that's what Bob always will send. And then Alice would always just decrypt it and kind of answer in a normal way. However, now what Eve could try to do is capture one of those ciphertexts, let's call it C, and then kind of tweak the ciphertext a little bit to kind of form it to a ciphertext C prime. And then it will send this ciphertext C prime to Alice. Alice will decrypt it. And then Alice will do the standard check of whether or not this is actually a well-formed message. And then there are two cases. Either C prime decrypts to something, to message M, that is well-formed, or not. And through this, Eve may not know what's the original message inside this ciphertext C. So not at all. It just would know that it's a valid JSON document. However, she may cleverly choose the C prime in order to gain information like, if the original plaintext looked like this, and I changed this in the ciphertext, then the changed ciphertext should also be well-formed. And then she would be able to use this oracle whether or not something is well-formed, so whether or not Alice actually answers to the message or just discards it as garbage. Alice would be able to use this information in order to kind of slowly get closer to knowing the original message. So this is a rough overview of why this actually makes sense. So the idea is that in this security game, we just give the adversary the ability to ask for decryption, so to actually get the complete plaintext, in order to cover also scenarios that are more realistic, right? Where Eve wouldn't get the complete plaintext, but just some information about the plaintext that's inside of tweaked ciphertexts. So basically here we're just doing a little bit of overkill in the security definition in order to cover lots of attacks. And this actually, in practice, this has worked out pretty well so far. So all of the attacks that we know against CPA secure encryption schemes, there's a whole bunch of those that are basically CCA attacks. So an adversary would kind of try to change ciphertext and learn information about this. There are a lot of practical attacks this way. And well, those would all be covered by this CCA security definition. So this is like the high-level overview why this makes sense. We will release a type 2 exercise next week where you can actually try this. So let's talk about some concrete examples of encryption schemes. Let's start with this one, where I basically take two CCA secure encryption schemes, and then the ciphertext of this new scheme that I'm creating, it will just contain of two ciphertexts, one for the first encryption scheme and one for the second encryption scheme. And then whenever I decrypt, I just decrypt both of these ciphertexts, and then if the two messages match, then I output this message. Otherwise, I will output an error symbol. And now my question would be, is this encryption scheme CCA secure, assuming that the two pi1 and pi2 are actually CCA secure themselves? So have you thought about it? Interestingly, this is not CCA secure, which is maybe kind of weird, because if you did this for two CPA secure schemes, then the result would actually be CPA secure, which is kind of intuitive, because if I give you two secure ciphertexts of something, then, well, it doesn't help you much more than just one secure ciphertext. However, for CCA, the situation is a little bit different, because you can circumvent this restriction that you're not allowed to query the decryption of the challenge ciphertext using this particular structure of the encryption scheme. So, do you have an idea for an attacker that can actually break this encryption scheme in a CCA attack? So one easy way to do it would be to ask for the encryption of 0. And I'll call this ciphertext C0. Then I would just output the two messages in 0 to the n, and 1 to the n. The concrete messages don't matter too much. Then I would get the challenge ciphertext C, which is an encryption of either 0 or 1. And now what I do is I ask for the decryption of ciphertext that I will prepare myself now, which consists of C1 in the first component and C20 in the second component. And then I get a result from that, a decryption result, and this will either be the error symbol. If it's the error symbol, then I would know, okay, this C1 here does not encrypt 0, because this is how the error happens. And the other possibility is that I actually get 0 as a result, and in that case I would know that also C1 encrypts 0, in which case, well, I would just output 0, and then I just perfectly know which one of the two messages it is. So the only thing that I have to make sure here is that the ciphertext that I'm querying here, this is not allowed to be the same as the challenge ciphertext C. How can it happen? Well, the first component is already the same in both. The second component, I claim, is usually different because it's a randomized encryption scheme. Also, if those two were the same, then I would immediately know that the encryption was of 0. So if C2 was equal to C20, then I'm not allowed to do this decryption query. However, in this case, I already know that the whole encryption will be of 0, because, well, this is an encryption of 0, so this must be an encryption of 0 too. So then I just, also output 0 as my solution. And then that's already it. So essentially, you can break these two CCA secure schemes if you combine them in this way by, well, just abusing the decryption queries and using that you can actually ask these decryption queries on kind of mostly the challenge ciphertext by cleverly recombining it with something you've seen before. So let's take a look at one more encryption scheme. This one is a little bit more complicated, I guess, but it's not that difficult. So for this encryption scheme, we start by taking a PRFF, and then this whole encryption scheme is supposed to be an encryption scheme for single bits. So I only want to encrypt either 0 or 1. So this is a fixed length encryption scheme for messages of length 1. Then key generation outputs a random key for the pseudonym function. And our ciphertext will actually be such that if I apply the pseudonym function to the ciphertext, then the least significant bit of that will actually be the message that I wanted to encrypt. To encrypt something, I sample random C. I check whether or not the image of C under the pseudonym function has the correct least significant bit, so either 0 or 1, depending on whether or not I want to encrypt 0 or 1. And then I output that pre-image of the pseudonym function. If this doesn't work, then we try another C until we find one that works. And yes, this is not strictly an encryption scheme for our definition of encryption schemes that we had in the lecture, because this encryption procedure here, it may actually run, in theory, it could run forever, but it's an encryption scheme where the encryption algorithm has expected polynomial runtime. And then this should be fine. So let's pretend our definition of encryption schemes allowed for expected polynomial runtime for encryption. So what do you say? Is this encryption scheme that we have here, is it CCA secure or not? So I'll give you another minute, but if you're stuck, the thing you should be thinking about is, if I get this challenge ciphertext, can I kind of tweak it in order to get any information about the least significant bit of the pseudonym function value of that ciphertext? So if I change C to C prime, can I learn something about M? So I hope you've thought about it a little bit, because I think it's good practice to think about these things. The solution is actually that this is indeed a CCA secure encryption scheme, assuming that F is a pseudonym function. And the intuition is actually, if I get the challenge ciphertext C, then I may try to tweak it to some ciphertext C prime. But then if this one here, if Fk of C actually, or the least significant bit of that, was actually 0, for example, then what is the least significant bit of the pseudonym function value of C prime? So the correct answer is that those two don't correlate at all. So let's say this is a secure pseudonym function, then we can in our head kind of think about this like an actual random function, small f. And if we think about it as an actual random function, then querying this random function at C prime and getting, let's say, 1, that doesn't tell us anything about querying this function on this different value C, whether or not this will have least significant bit 0 or 1. So our chances after observing, let's say, this part here, our chances of observing that this is 0 is just 1/2. So essentially, if I take a random function, then the least significant bits of like arbitrary values, they don't correlate at all. They are just random. So I don't want to do a full proof of this, but what would the proof look like? What's kind of the structure? Do you have an idea? Well, this is a pseudonym function again. So the strategy that we had for encryption schemes based on pseudonym functions should also work here. So the first step would be to come up with a conceptual scheme that is kind of this original scheme pi, but just we replace all of the invocations of the pseudonym function by invocations of an actual random function that we just store in the key. And then this is a conceptual scheme because, well, we can't actually store full random functions in the key, that's too large. But yeah, never mind. So all of this, the standard structure that we had so far multiple times in this whole course. And then we show again that if we had an adversary that can win more in this encryption scheme pi than in the encryption scheme pi concept, then this would give rise to a distinguisher between the pseudorandom function and the actual random function. Then we do this reduction, etc., etc. So in the end, we get something like, very informally now, that this scheme here behaves for someone who goes through the CCA experiment. It looks almost the same as the scheme pi. And then we're just left looking at the conceptual scheme pi concept. And now roughly let's look at what are the chances of an adversary winning the pi concept, the CCA game against pi concept. For this, we should we look at the change suffix c, and as at basically the value of c under the random function. And then we argue that the view of A is actually probably independent of f of c. And this is unless we have chosen C before in any of the encryption queries, or if A has ever submitted a decryption query for C. But because we choose C uniformly during the encryption, the likelihood of this is kind of negligible. Note that for encryption, it's kind of the same argument that we did last time for the for this encryption scheme, the CPA one that we had in the lecture. For decryption, there's a little bit of refined analysis, I guess, because there's this phase one that goes until A outputs the two ciphertexts, the two plaintext messages, M0 and M1. And there A may actually ask for arbitrary C. So decryption is of arbitrary C, and then in that case it would learn the least significant bit of f of c. There we would use that only after A outputs these two messages. A would learn this random C. So something happens, we don't know with what distribution. A may like always query 0 through 20. But then we choose the C randomly during encryption of the bit MB, and then C is given to A. And then afterwards, A is just not allowed to query for decryption of C anymore. And then like the analysis is always just the same as for encryption, that we never like hit this C a second time. So now this is actually difficult, but it's also not all that interesting, so I'm leaving it out. So overall, this happens with negligible probability. So overall, in most of the cases, the view of A is independent of f of c. And then, well, the probability of A guessing correctly, which is what is the least significant bit of f of c, is just 1/2. And then we have shown that this whole scheme is just CCA secure. At least we have sketched it. Okay, this is it for CCA secure encryption. Thanks for your attention. See you.